Let us solve one more problem on symmetrical fault analysis where we have to consider the pre-fault load current also. A generator is connected through a transformer to a synchronous motor. The subtransient reactances of generator and motor are 0.15 and 0.35 respectively. The leakage reactance of the transformer is 0.1 per unit. All the reactances are calculated on a common base. A three-phase fault occurs at the terminals of the motor when the terminal voltage of the generator is 0.9 per unit. The output current of the generator is 1 per unit and 0.8 leading. Find the subtransient current in per unit in the fault, generator and motor. Use the terminal voltage of the generator as reference vector. So let us draw the reactance diagram first. Generator is connected through a transformer to a synchronous motor. So a generator, transformer and a synchronous motor. Generator, a reactance in series with a voltage source. Then a transformer is represented as a series reactance. And finally the motor as a reactance in series with a voltage source. So this will be the reactance diagram, and the reactances are already given and it is specified that they are expressed on a common base. So the reactances expressed on a common base are directly given. So we just need to mark the values. Reactances of generator is J0.15, that of motor is J0.35, J0.35, that of the transmission line is, the transformer is J0.1 per unit. A three-phase fault occurs at the terminals of the motor. So here fault is on the motor terminals. So fault will be occurring at this point. So we need to calculate the pre-fault voltage at this point, ETH at the motor terminals. Now the terminal voltage of the generator is given. When a three-phase fault occurs at the motor terminals, the terminal voltage of the generator is 0.9 per unit. So the generator terminal voltage is 0.9 per unit. The output current of the generator is 1 per unit. So here the output current of the generator or the load current is directly given. IL, the load current is directly given and is equal to 1 per unit. And 0.8 leading. So power factor is given. So angle of the load current will be cos inverse 0.8, that is 36.86 degree. And it is leading, so angle plus 36.86 degree. So load current is directly given here. Find the subtransient current in per unit in the fault, generator and motor. So we have to calculate the total fault current, the total current in the generator and the total current in the motor. And it is given that we can use the terminal voltage of the generator as the reference vector. So the terminal voltage of the generator is the reference. So we can mark it as 0.9 angle 0 per unit. Okay. So these are the various parameters given. Now we have to calculate total fault current. So total current flowing to this towards this fault point, and total current in the generator and in the motor. So fault current will flow from generator towards the fault point, it is IFG, and fault current flowing from the motor towards the fault point is IFM. Also load current will flow into the motor, that is IL, which is given as 1 angle 36.86 degree. Now as all the reactances are given in per unit, we don't have to calculate the reactances. We can directly move on to the calculation of fault current. So we know that fault current is equal to fault current IF is equal to pre-fault voltage at the fault point divided by Thevenin equivalent reactance as seen from the fault point. So ETH, see here the pre-fault voltage at the fault point is the motor terminal voltage. So we have to calculate the terminal voltage of the motor, and for that here the generator terminal voltage is given, and we also know the load current. So if we add the voltage drop across this reactance, that is transformer reactance, to the generator terminal voltage, if we subtract the voltage drop across the transformer reactance from the generator terminal voltage, we will get the motor terminal voltage. So motor terminal voltage ETH will be equal to the generator terminal voltage, that is 0.9 angle 0, minus voltage drop across this transformer reactance, that is IL into J 0.1, that is 1 angle 36.86 into J 0.1, and this will be equal to 0.9633 angle minus 4.8 degree. Okay, so we got the value of ETH. Now we have to calculate XTH, which is the Thevenin equivalent reactance as seen from the fault point. So if we look from this fault point, these two reactances are in series, and that series combination is in parallel with this reactance. So these two are in series, which is in parallel with this one. So the Thevenin equivalent reactance XTH is equal to 0.35 J 0.35 parallel to this one, parallel to J 0.1 plus J 0.15. J 0.1 plus J 0.15 parallel to J 0.35, and the answer will be J 0.1458 per unit. So we have ETH as well as XTH. Now the fault current IF will be equal to ETH by XTH, that is 0.9633 angle minus 4.8 degree divided by J 0.1458, which is equal to 6.606 angle minus 94.8 degree per unit. So this is the value of total fault current. So we have been asked to calculate the total fault current, the generator current and the motor current in per unit. So we got the fault current in per unit. Now we need to calculate the total current in the generator in per unit. So we know that the fault current is flowing out of the generator terminal, and also the load current is flowing out of the generator terminal. So total current of the generator will be the phasor sum of fault current supplied by the generator and the load current. So we need to calculate the fault current supplied by the generator, IFG. So fault current supplied by the generator, IFG, will be equal to, so we know that this branch is in parallel with this branch. So we can calculate IFG using current division rule. We know the total fault current, this branch is in parallel with this branch. We know the total fault current, current flowing through the fault point we know, and then by using current division rule we can calculate this IFG as well as IFM. So IFG will be equal to total current into total fault current into IFG. If we have to calculate IFG, it will be equal to total fault current into opposite branch reactance divided by total reactance. So IFG will be equal to total fault current, that is 6.606 angle minus 94.8 degree into opposite branch reactance, that is J opposite branch reactance is J 0.35 divided by sum of reactances, that is J 0.35 plus J 0.1 plus J 0.15, that is J 0.6. So on multiplying, the answer will be 3.8535 angle minus 94.8 degree. So we got the fault current supplied by the generator. So next we have to calculate the fault current supplied by the motor. So this can also be calculated using current division rule. So total current into, so we have to calculate IFM, current supplied by this branch, current flowing through this branch. That will be equal to total fault current into opposite branch resistance, that is J 0.15 plus J 0.1 divided by sum of resistances. So IFM, fault current supplied by motor, IFM will be equal to total fault current, that is 6.606 angle minus 94.8 degree into opposite branch resistances J 0.1 plus J 0.15, that is J 0.25. divided by sum of resistances, that is J 0.6. So on solving, we will get the value of fault current supplied by the motor as IFM is equal to 2.7525 angle minus 94.8 degree per unit. Okay. So now we have to calculate total current supplied by the generator and the total current supplied by the motor. Total current supplied by the generator, that is IG is equal to the sum of fault current supplied by the generator and the load current IFG plus IL, which is equal to 3.853 angle minus 94.8 plus the load current, that is 1 angle 36.86 degree, and the answer will be 3.274 angle minus 81.6 degree. Okay. So now let us calculate the total current supplied by the motor. So total current supplied by the motor IM will be the phasor difference between the fault current supplied by the motor and the load current, because fault current is flowing out of the motor terminals and load current is flowing into the motor terminals. So this will be 2.7525 angle minus 94.8 degree minus 1 angle 36.86 degree, which is equal to 3.498 angle minus 107.1 degree per unit.